Hello calculus fans, and welcome to section 3.8 part 2, where we cover Newton's law of cooling. Newton's law of cooling states that the rate of cooling or warming, it works for cooling and also for warming, but the rate of cooling or warming of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. And it does have limits. It fails to predict accurately if the difference is too large, but we're not going to worry about that for now. And Newton's law of cooling can be expressed as a differential equation. So again, we've got an equation as a derivative, so it's a differential equation. And just to point out all the variables here, so this T sub S, this is the temperature of the surroundings. And this has to be a constant. Okay, so it's got to be a constant to make this work, or at least very close to constant. Okay, capital T, the capital T here and here, capital T is the temperature of the object. All right, and then we have got little t here. Of course, this t is just time, right? So capital T is not the same as small t, right? They're different. This is temperature and this is time. And then as a little note here, capital T, which is a function of small t, right? Temperature is a function of time. So capital T is the temperature of the object at time t, little t. Now this differential equation may look familiar. It's very close to something else we've seen. So just another little note here, we could say that if dy dt equals k times y, we've already seen this one, then the solution is y of t equals y of 0 e to the kt. So we've been working with this one already in this section. This is a differential equation. The solution to this differential equation is this. And this differential equation is just basically stating that the rate of change of y is proportional to y itself. And those are the types of things we've been working with in 3.8. Well, this looks fairly similar. We've got this change in temperature with respect to time, and it's proportional to the difference, right, between the temperature of the object and the temperature of the surroundings. So it sort of looks like a familiar format. So if we were going to solve this, we're going to solve this new differential equation, what we need, we could say we want this dt, d little t, to be in the form dy dt equals ky. Why do we want that? Because we know how to solve this. We have a solution for this. So if we could make this thing look like this, then we could solve this new differential equation also. So that's what we're going to do. We're going to let this difference just be y. Okay, so we're just going to let that happen. We're just going to say, let's let y equal t minus t sub s. We'll just let y equal this. This is going to be part of our solution to these differential equations. So in other words, what this means is that y of t equals t of t minus t sub s. And then if we were to differentiate this equation, then what we would get is y prime of t equals t prime of t. And then the derivative of this is just the temperature of the surroundings, which is a constant, so the rate of change would be 0. So we get this. So then if we rewrite this with Leibniz notation, we could say dy dt equals dt dt. And we know from looking above that the original equation here that we're working with, we're going to just write what this is equal to. Okay, so what that's equal to from looking above is just k times t minus t sub s. And then t minus t sub s is just y. So this is equal to ky. So basically we have dy dt equals ky. So then what we can do is we can just use this to find y. And then once we have y, then we can find t because we can go back to this equation. Okay, so when we're solving these problems for Newton's law of cooling, it'll look familiar because we're going to first solve an equation that we've been solving all along. We'll solve this differential equation after we do a substitution, and then we'll do the substitution again in the other direction to find t. Okay, so this is sort of the process we use whenever we use Newton's law of cooling. Now I know as soon as you guys see a new formula, the first thing you want to do is try it out, right? So without further delay, here is our first question. Example 7 says we've got some soda in the refrigerator. So let's say we've got a 12-ounce soda with a temperature of 72 degrees Fahrenheit, and it is taken from the carton and placed into a refrigerator where the temperature is 38 degrees Fahrenheit. After 10 minutes, the temperature of the soda has cooled to 65 degrees Fahrenheit. Question A says, what will the temperature of the soda be after 20 minutes? All right, this was a real-world problem taken. One time I had to prepare for a faculty meeting, and these things can be extremely painful and boring. So I had a Diet Coke with some Jack Daniels added to help dull the pain of the meeting, and took these measurements to get ready for this problem. I'm kidding, of course. I don't like Diet Coke. But let's try this problem out. Start off with our equation, our differential equation, and look at what this says. What it really says is the change in temperature, right? The change in temperature is proportional to the difference in the temperature. So the temperature will change faster when the difference is great, right? Because it's proportional to this. And then what we said we're going to do is we're going to let y be this. So just to get started, let's let y be this. Okay, so that gives us this. And I'm just going to fill this in. You know, so it's y of t equals t of t minus t sub s. Remember, this is the temperature of the surroundings. So if this is true, then that also implies that the temperature is equal to t sub s plus y of t. And these are what we're going to need. So we're going to do this substitution first. And that's going to allow us to solve for y of t. And then from there, we'll get what we really want, which is t of t. Okay, so every time we use Newton's law of cooling, we can just make this substitution and then substitute back. So when you start this problem, we need to look at the initial temperature. So we've got this 12-ounce soda. Initially, it had a temperature of 72 degrees Fahrenheit, right? And then we place it into the refrigerator, and then it says after 10 minutes, the temperature of the soda has cooled to 65 degrees. So we've got our initial temperature at time 0. Then we've got our temperature 10 minutes later, 65 degrees. And this is the temperature of the surroundings, right? The refrigerator has a constant temperature of 38 degrees. So let's write these down. So to get started, we'll say T of 0 is 72. Okay, T of 10 is 65. Temperature of the surroundings is 38. And what we want to know is what will the temperature of the soda be after 20 minutes. So we're looking for what's temperatures after 20 minutes. So we want to know what is this going to be. All right, so once we write down our givens here, we want our initial temperature. We need one reading, X amount of minutes or hours later, depending on the situation. And really what we really need is these two initial, we need the initial condition and one more data point. That's really along with the temperature of the surroundings. And then we can use Newton's law of cooling to predict other, a temperature at a different time. So we always start off with the two data points that will be given. And then we're going to do this. We're going to convert these T values, these temperature values, to Y values. Okay, so I'm going to use this to do that. So I immediately go from T to Y. So I go Y of 0. So I have T of 0 and I need Y of 0. Well, y is just t minus t sub s. So this is going to be t of 0 minus t sub s. So t of 0 is 72 minus 38. So this is 34. So y of 0 is 34. And then I also need y of 10. So whatever these two times are for t, I do the same thing for y. Okay, so y of 10 is going to be t of 10 minus t sub s. Again, I'm just using this equation right here, this substitution. We're letting this thing be y. So that's going to be 65 minus 38, and that is going to be 27. Okay, so once we have these two data points, then we're going to, it's almost like the problems we did previously, the radioactive decay, those kind of problems. We solve a problem like that. So from here, we're going to take this and go back to this. Y of t equals y of 0e to the kt. So we use that same equation we used before, and now we just plug in some data. So y of 0, that's 34, and then when t is 10 minutes later, then our y is 27. So we just plug in the information here. So 27 equals 34e to the k times 10, and then we solve this for k like we normally would. Divide each side by 34. You get e to the 10k. Now that this base is by itself, I can take the natural log of each side. So I take the natural log of 27 over 34 equals the natural log of e to the 10k. Now we're going to use that rule of logarithms that we used a lot already. So this is going to come down. And we get natural log of 27 over 34 equals 10k times the natural log of e, but I already know the natural log of e is just 1, right? So we've got 10k, of course we just want k, so I'm going to multiply each side by 1/10, and that would give us k is equal to 1/10 times the natural log of 27 over 34. So once we've got this, we can go back up here and come up with our model. So we could say, I guess I'll keep going right here. So y of t is equal to, well, y of 0, that is 34, e to the kt. Okay, so here's k. I'm going to switch these around though, because I want to get that cancellation that we've been using so much. So I'm going to write this as natural log 27 over 34 times 1/10, and then that has to get multiplied by t also. All right, so this will be familiar. This is what we've done in the past when we were working on the part 1 of this section. So I'll write e to the natural log 27 over 34 times 1/10 times t, which is the same as times t over 10. And then we'll do that same thing before, where we think of this right here and do this e to the natural log of x equals x, right? So we can simplify this and write y of t equals 34 times 27 over 34 raised to the t over 10. So that's y of t. So once we have y of t, then we look up here, right? T of t is just the temperature of the surroundings plus y of t. So here's y of t, temperature of the surroundings is 38. So now we have our model. So our model that we want is the model for the temperature at time t. That's just going to be 38 plus what we just found, 34 times 27 over 34 raised to the t over 10 power. Okay, now sometimes the temptation is great here. That's a 34, that's a 34. They cannot cancel, right? This is a base. This is not. This is 34 times this, right? So this is our model. So that 34, that's 34. It's a little bit hard to see, but this is our model now for the temperature at any time t. All right, so we can use this now. So our question originally was, what would the temperature of the soda be after 20 minutes? Well, now it's easy. Now that we have this, we can say, all right, so t of 20 is 38 plus 34 times 27 over 34 raised to the 20 over 10, which is basically just squared, right? So 1 time is 20. I put a 20 in for a t, so I have 20 over 10, which is 2. And then if you punch that in your calculator, you will get approximately 59 degrees. I just run it to the nearest degree. So once we have this, then we can answer any of their questions, including this next question. How long will it take for the soda to cool to 40 degrees Fahrenheit? Well, they're asking for the time now, right? How long? So we need to find the time. So to find the time, if we look back here, we have to solve for t, right? How long will it take? So we solve for t. So the 40 is the temperature, right? So 40 goes here, and then we solve for t. So to solve this one, we just have 40 equals 38 plus 34 times 27 over 34 raised to the t over 10. Now, if you love algebra and you love logarithms, you are going to love this next part, because there's a lot of algebra and a lot of logarithms in this section. So we just go through and solve for t, but what you should do is press pause and try it yourself. Don't just sit there watching me do it. I can't do all the work. You got to do some of the work too. As you know, the only way to get better at calculus is by doing calculus, not just by watching me. Right? Think how easy life would be if you could get really good at basketball just by watching NBA games. Next thing you know, you're in the league. That'd be awesome. We'd all be very wealthy, but it doesn't work that way with basketball or calculus. So practice. You got to try it, okay? Press pause, try it, and then come on back. Okay, welcome back. Hopefully you tried it out. So what we need to do, get t by itself, I'm just going to first subtract 38 from each side, right? Got our equation here. Subtract 38 from each side, and that would leave me with 2 equals 34 times all of this. Then essentially I need to get at this. So I need to take the natural log of something, right? Or common log, any base log, but I just always use natural log. But I can't do it now because I've got this 34 here. So I'm going to divide this side and this side by 34 to get rid of that 34. Right, so I divide each side by 34. That will give me 2 over 34 equals this. And then this is really just 1 over 17. So I'll do that. I'll reduce that. And now we're ready to take the natural log. I can take the natural log of each side because that will allow us to get at that. So if you take the natural log, I'll write this as 1 over 17 at this point, equals the natural log of this. That will allow this to come down, and that would give us natural log of 1/17 equals t over 10 times the natural log of 27 over 34. Okay, now we've just got a lot of algebra. So I'm going to first just divide each side by this natural log. All right, divide this, so that'll leave us with t over 10. So if I do that, we get natural log of 1 over 17 divided by natural log of 27 over 34 equals t over 10. Now, sometimes students will ask, like, do I have to keep going with this exact value? You really don't. Just be careful. So, again, we don't cover significant digits in here, but you don't want to get round off errors. So you don't want to, like, round the second decimal place and then think that you're going to get an answer that's any good, right? So if you do use decimals, just keep a lot of decimal places and then round at the very end. That'll eliminate round off errors. Okay, so you don't have to keep the exact values like this. All right, so from here we're almost done. I just need to get rid of this 10. So we do a little algebra, multiply this side by 10, which I can do as long as I multiply that side by 10. That cancels, and we'll finally get 2 equals natural log of 1/17 divided by the natural log of 27 over 34 times 10. And if you punch that in your calculator, you will get right around 123 minutes. Okay, so hopefully that worked out okay. Hopefully it makes sense. And we'll maybe try one more just to give you one more shot at one of these. Okay, I found one I think you guys are going to like. It's number 16 in the book. And this is number 16 in the 8th edition and also in the 9th edition. And it's about a murder investigation. Very exciting. Murder investigation. First, we have to talk about something, though. Let me mention something. Let's say the current time is 5:32 p.m. This is the current time. Okay. And we need to figure out what happened in 3 hours. What time was it 3 hours and 44 minutes ago? So we go, I'm going to subtract 3 hours and 44 minutes. All right, so this was, I'll say, 3 hours, 44 minutes ago. We need to know what time was that. Okay, I just want to make sure we're okay with this borrowing that we're going to have to do. So when we're subtracting, this over here is minutes, right? There's 60 minutes in every hour. So we have to keep that in mind. So when you subtract here and you're like, oh, I have to borrow. Well, when you borrow from this 5, I take 1 hour off of here. So when I go, okay, I'm going to make this 4 instead of 5. And then when I bring this over here, I'm adding 60 minutes onto this, right? So this ends up being like not 432, but when I add on, I'll get 492, right? It's sort of like 92 when we're borrowing. Because remember, we're going from hours to minutes, just to keep in mind. And then when we subtract here, we can treat these just like regular base 10 numbers. These are all minutes, right? 92 minutes take away 44 minutes. So there we borrow like we normally would. So I'm going to borrow from this 9, make it an 8, make this 2 a 12. And then when you subtract 12, take away 4, you get 8. 8 take away 4, you get 4. And then we just subtract like normal over here. And we get 1:48 p.m. Okay, so now we are ready for this problem. So here's what it says. It says, in a murder investigation, the temperature of the corpse was 32.5 degrees Celsius. So let's write down what we've got. It was 32.5 degrees Celsius at 1:30 p.m. 32.5 degrees Celsius at 1:30 p.m. And it was 30.3 degrees Celsius an hour later. So it's cooling off. I'll say 1 hour later. Okay, normal body temperature is 37 degrees Celsius, 37.0 degrees Celsius. So we could say like when alive, right? I'll just say normal body temperature. Okay, so we're kind of assuming that was the initial temperature. And the ambient temperature was 20 degrees Celsius. So the temperature of the surroundings is 20 degrees Celsius. The question is, when did the murder take place? So there's a couple ways to go after this problem. One way is more difficult, though. So let me just tell you the more difficult way. The more difficult way is to treat this as time 0, because then we've got a couple of data points here. You end up needing a variable. It's going to be much easier just to count this initial temperature reading as time 0, and then we can count this as time 1, like 1 hour later. Or if you wanted to use minutes, we could count it as t of 60, and then we'll just have to go backwards. So we'll go back to figure out when the body was 37 degrees. So we'll get like a negative time. So it'll be a little weird having a negative time, but it'll be much easier than having variables introduced. So what I'm going to do is call this our initial temperature. Okay, so this is what we've got. T of 0, T of 1, I just went with hour. 1 hour later, right, 1 hour later, it's 30.3 degrees, and the temperature of the surroundings is 20. So remember, this is Newton's law of cooling, so I'm going to write down what we always use with Newton's law of cooling. We say, okay, dt, d little t is K times T minus T sub S. And every time we do that, we're going to let Y be this. Okay, so then we're going to say, let's let Y equal this. And that implies, of course, that T sub T equals T sub S plus Y of T. So we're going to do this, and then once we solve for Y, we'll have this. Okay, I'm not sure why I didn't put the little the independent variable in here, but okay, so there we go. So we're going to use this to get our Y values, right? So we've got our T values, we need our Y values. So this is Y of T equals T of T minus T sub S. So we've got T of 0, so let's find Y of 0. Y of 0 is going to be T of 0, which is 32.5, minus T sub S, which is 20. So that's going to give us 12.5. And then Y of 1 will be T of 1, which is 30.3, minus T sub S, which is 20. And this gives us 10.3. So we're just doing exactly what we did last time, right? We're just using this. We're taking these temperature readings, which I'll just refer to as T values. We convert those to Y values. And once we have these, then we can do like what we've done before. Y of T equals Y of 0 e to the KT. So if we fill in these blanks, we know that T is 1, right? We know the initial Y value is 12.5, but when T is 1, the new Y value is 10.3. So we have 10.3 equals 12.5 e to the K times 1. So this is going to be kind of a nice one because time is just 1, so it makes it a little easier. Okay, so then we want to solve for K, so I need to divide both sides by the 12.5 so I can isolate that K, or isolate the base E. And now to get at this, we do the same as always, take the natural log of each side. So you get the natural log of 10.3 over 12.5 equals the natural log of e to the t. And then, of course, this allows us to then bring this down. So we get the natural log of 10.3 over 12.5 equals t times the natural log of e, right? T times the natural log of e, but the natural log of e is... Did you just say 1? I think I heard you say 1. Okay, I think I did. Pretty sure. Natural log of e is just 1. So this gives us our t value. Once we have that, we can plug it in up here, right? So we can come up with our equation for y. So now we know that y of t is equal to y of 0, which is 12.5, e to the k in k. Oh my gosh, do you guys see what I just did? Were you yelling at the screen? I hope you were. Look at this. What happened? What happened here? Some weird thing happened. I think it was a computer glitch, obviously. It must have been a computer glitch. Yes, that T should not be a T. That should be a K. Oh my gosh. Don't get old, okay, guys? Don't get old. Nothing good happens when you get old. Okay, so that was supposed to be a K here, and then this would be a K, right? T is 1. Oh my gosh. Sorry about that. For those of you who were screaming at your computer monitor. Okay, so we're okay now. So we have 12.5 e to the K times T. Here's K. E to the natural log of 10.3 over 12.5 T. It's one thing about making a video. If I do this in the classroom, do you think students usually say, "Hey, wait," or do they wait till I get all the way to the end, and then they say, "You messed up on step 1"? Sometimes that happens, but I know you guys would not do that to me, right? You tell me right away. Okay, so those who are yelling at me on your computer screen, I appreciate that. All right, but anyway, we fixed our mistake here, well, my mistake, and we've got this right here. Now we can clean this up, right, just like always, to make it a little neater model. We're using the same as always, e to the natural log of x equals x. No matter what you put here, it's the same, right? So e to the natural log of this thing is really just that thing. So we get y of t equals 12.5 times 10.3 over 12.5 raised to the t. Remind me again what you would never ever do right here. Are you reminding me? You would never cancel, right? This is a base. The base raised to the t power. So you can't cancel through there. Okay, but that gives us y of t. If we have y of t, we can definitely get to t of t. So let's put the pieces together here. What we're really looking for is a model for the temperature at any time t. So that is going to be t sub s, which is 20, plus y of t, which is 12.5 times 10.3 over 12.5, all raised to the t. So this is our model for the temperature at any time t. So then the question was, when did the murder take place? Okay, so when the murder takes place, what we can do is just plug in the temperature of a living body, right? Which they said is 37 degrees Celsius, normal body temperature. So we can say, if this temperature is 37 degrees, what was T? Now remember, we're going to go back in time because we're starting at time 0 after this murder took place. So we're going to get a negative value for T. So we'll just have to walk back from the initial reading that happened at 1:30 p.m. All right, so let's plug in the temperature of 37 and then see what happens here. Okay. All right, so here is your chance. Let's see what you get. So press pause, try it out, and then check back. Okay, so hopefully you did that. Hopefully you tried it out. And let's see, so we're going to need to subtract 20 from each side first, right? So I'm just going to subtract 20 and move this up a little bit. I never know exactly how this is going to appear on the screen. So hopefully everything is fitting just fine. So subtract 20, I get 17 equals 12.5 times 10.3 over 12.5 raised to the t. Now I need to divide each side by 12.5 to get 10.3 over 12.5 raised to the t. And now we're back where we've been a whole bunch of times. We need to get this t out of here. So I'm just going to take the natural log of each side. So take the natural log of 17 over 12.5 equals the natural log of 10.3 over 12.5 raised to the t. Now at this point, this t comes down. And we get the natural log of 17 over 12.5 equals t times the natural log 10.3 over 12.5. And now we're almost done. If we want to get t by itself, we just divide each side by this thing. And we'll get t equals the natural log of 17 over 12.5 divided by the natural log of 10.3 over 12.5. And when I punched this in the calculator, what I got was negative 1.588. Oh, let's just go 4. I'll go to that. I'll go to the fourth decimal place. Again, we don't cover significant digits here, so I'm just going to use a lot of decimal places and round at the end. And someday when you're in physics or chemistry, you're going to learn, your physics or chemistry professor will try to convince you that 2 times 6 is really 10. What? But in calculus, when we don't study significant figures, 2.6 is still going to be 12 for us, okay? But that's something you'll see later. Okay, but back to our problem. So we've got this time. So we need to figure out, basically, this time is in hours, right? I know it's in hours because our inputs were in hours, right? Because look back at our inputs here. Our input here was 1 hour later, right? So our inputs are hours, which means that this is going to be a number of hours. So the time is negative this many hours from our initial reading. Our initial reading took place at 1:30 p.m. Okay, so 1:30 p.m. We need to think about, we have this many hours before 1:30 p.m. All right, so I'm going to do it this way. I'm going to go back 1 hour, right? I'm going to go back 1 hour. 1 hour from 1:30 p.m. would be 12:30 p.m., right? Just after noon, right? 30 minutes after noon. But that still would leave us with this many hours to go back, right? Because it's negative. So we need to convert that to minutes. Well, how do we convert minutes to hours? Well, we take the hours, multiply by 60, right? If I multiply 0.5884 by 60, I get about 35.304. But I'm just going to go with 35. So it's 35 minutes, which makes sense, right? Because 0.5 hours is just over half an hour, right? Half an hour is 30 minutes, so it's just over that. So basically we need to go back now 35 minutes. So 35 minutes before this. Well, 30 minutes before this was noon, right? 12 o'clock. 5 more minutes back. That's going to put us at 11:55 a.m. Right around there, according to our readings, is when that murder took place. Okay, and now you are officially qualified to help out the police. So let's say you're walking home from class today, and you know how you are, you always have your calculus book with you, and you go by a house and you see a lot of police cars around and sirens going, and you see this police tape. It says crime scene, do not cross. Well, that doesn't apply to you anymore. You can officially just go right underneath that crime scene tape, and when the officer approaches, just say, "Don't worry, officer, I'm here and I know calculus. Point me to the body, please." And you should be all set. I'm sure they would love to have your input on the crime. Okay, now, that might fall under bad advice. Probably do not want to do that. But you are definitely qualified to solve these kind of crime scene problems in your calculus textbooks. And there is one more problem that we should take a look at, and that is problem number 20. This one has to do with compound interest. It's number 20. The 9th edition says, what we're going to do is just 20 part A. Okay, 20 part A. It says we've got $2,500 borrowed at 4.5% interest. So we're going to borrow $2,500 at 4.5% interest. It says find the amounts due at the end of 3 years. So we're going to borrow this for 3 years. If the interest is compounded, and it's got a whole bunch of differences here. So they've got annually, quarterly, monthly, weekly, daily, hourly, and continuously. All right, so let's figure this out. Well, first, we need our compound interest formula, which you've probably seen plenty of times. So the compound interest formula, well, P is the principal. It's the amount that we're going to borrow. And then the amount here, this is the amount that this principal will grow to over time. t is the time always in years. So this has to be in years. So if we had borrowed this for 6 months, t would be 0.5, right? Time is always in years. R is the rate, always as a decimal. So although we'll say 4.5%, we're not going to put 4.5 in there. We have to put 0.045 in the formula. The formula always gets a decimal. And then n, this is the number of compounding periods per year. Okay, so for most loans, that's going to be 12. It's compounded monthly, and this is one of those. Well, there's gonna be differences here in this loan. So most loans you get, car loans, home loans, student loans, number of compounding periods per year are 12. So, all right. So this is what we've got. Now also one of these says compounded continuously. So this is the problem where E comes up. We had mentioned this in class before. So as the number of compounding periods per year goes up and up and up, as it approaches infinity, then we'll get a new formula here. Then we get the amount is equal to P e to the RT. So this one is only when interest is compounded continuously. Okay, so as long as it's compounded anything other than continuously, we use this formula. All right, so to do this problem, we've got the first one says find the amounts due at the end of 3 years if the interest is compounded. The first one says annually. Okay, well, annually just means there's one compounding period per year, right? So this means n equals 1. Okay, the second one says quarterly. Okay, sometimes this software has a mind of its own. Quarterly. That means, of course, that n equals 4. Okay, and then let's see if I can put this back how it was. Let's see, the other one is monthly. So we're just going to sort of see if we can see what happens as this changes. This one is monthly, which is probably the most common one, which means n equals 12, right? 12 months in a year. And then we go on to this one. All right, I'm not sure what's happening with the software. Weekly. Okay, this would be n equals 52, right? 52 weeks in a year. Quarterly. Oops, what am I reading here? Hourly. Okay, so for this one, we have to do a little math, right? We could think of it like this. Okay, hourly. I'm going to think of it, well, I'm just going to go 365 days, right? 365 days times 24 hours in a day, and this would be 8760, right? So that's assuming a 365-day year. And then the last one is continuously, and this one, okay, we get our special formula. I think maybe my software is suddenly possessed. So continuously just means n equals infinity, and we get our other formula out, right? So for annually, when we set this up, we're going to have the amount equals the principal, which we said is $2,500. And then we've got 1 plus the rate, which is 0.045 over n, which is 1, raised to the n times t. Well, t is 3, so we have 1 times 3. So well, you just have to be careful with your calculator when you do these. So if, like, the newer TI-83s and 84s, or TI-84s at least, have a math print, or TI Inspire, or any of the newer calculators have math room, or this will be a superscript up here. If your calculator doesn't have that when you're doing these, make sure you put these in parentheses, okay? And you'll know because we should all get the same answers for these. So on this one, when I punch this in the calculator, I get, let's see, 1.045. So what I'm getting here is, remember this is money, 28.52. Okay, now we live on Earth, and when you use dollars on Earth, how many decimal places do you go to? 7? No, go to 2, right? Go to 2, so we have to round correctly. So I get 28.52.92 for this one. Okay, what that means is, if you look at this, the original loan was $2,500, so this person paid $352.92 in interest. All right, so now if we try quarterly, the thing that's going to change is n. So n was 1 here, so it's going to change to 4. So let's see what difference this makes. So this is the amount equals 2,500 times 1 plus 0.045 over 4 raised to the 4 times 3. And what I got was 28.59.19. So when you compound it quarterly, you make a little bit more money, right? Make a little bit more. And then monthly, so if you compound monthly, the amount here would be 2,500, 1 plus 0.045 over 12, raised to the 12 times 3. What I got here was 2860.62. Okay, so as the compounding periods go up, the amount goes up. So the question is, what's going to happen when it's compounding continuously? Is it going to go to infinity? We'll have to see, right? So we're at 2860.62. Okay, now we're to kind of a weird one, weekly. This typically means you're getting a bad loan if they start rounding like this. If they start using 52 compounding periods per year. But let's see. I think there was like payday loan places do crazy things like that. So this would be 52 times 3. Okay, so this one I am getting 2861.17. So it's sort of slowing down, right? It's 2860, 2660, going up, but not too much. Now hourly, that's a lot of compounding periods. Let's see what happens here. Amount equals 2,500 times 1 plus 0.045 divided by 8760 raised to the 8760 times 3. And what I get here is 2861.34. It's slowing down. I just realized I need my glasses. There's also a question about daily. So if you do daily, so if I had, there's one in here for daily, so then n would be 365. So let me just squeeze this in here. Daily, just so we can see the difference. So of course n would be 365. Daily, if you go through the math, you get 2861.32. All right, so here's weekly, daily, hourly. Not a whole lot of difference. What about continuously? Well, we get to use a new formula now. A equals P e to the RT. So the amount equals 2,500 e to the 0.045 times 3. And then you get, let's see, is it going to be a million? No, 2861.34. The change to the second decimal place is no change at all. So just to think about what's happening here, this is our compound interest formula. So as n goes to infinity, so when we have this continuous compounding, n goes to infinity. So what we really have here is 1 plus this r over n. R is a constant. So as n gets bigger and bigger and bigger, this goes to 0. So we have a base of 1, or a base that's approaching 1, and then this n goes to infinity. So we really have 1 to the infinity, which is an indeterminate form. So that's what's happening. We've got a indeterminate form, and then e makes an appearance in here. Okay, lovers of calculus, that should put you in a good spot to tackle the rest of these homework problems. So go ahead and give them a try, and you know what to do. If you're running any questions, let me know, and I will talk to you soon.